Hey everyone, so we're going to continue our discussion where we're going to start actually the next topic. It's the last topic for now, at least, for the AP Physics 1, which is all about rotational motion. So I had mentioned this before that one of the things about rotational motion that you're going to have to be aware about is that we're essentially going to go through all the other topics that we've done already, and we're going to pick out information and figure out how that can be related to motion. So, for example, we're going to talk about rotational motion. We're going to go back to forces and include forces and how that affects rotational motion. We're going to bring back momentum and energy and all that good stuff. So, as I jokingly say, we essentially are going to recap everything in the course all within 3 weeks. All right. So, let's consider this following case. Is this object moving? Yes or no? How do you know this object is moving? Now, if we went with our original definition of movement, movement was defined as the change in the position, either horizontally or vertically, that an object has. So if you have an object on a table and all of a sudden it moves, a meter to the right, or it moves above the table or something, we can tell that it moved because it is physically displaced. Now, unfortunately, this wheel, as it turns, doesn't actually do that. It doesn't move left and right. Instead, it rotates. We know it's moving, but we have to change our definition of what we consider movement. So again, before, displacement was considered the starting point and ending point relative to some origin section. Now what we're going to do is try to think if we can rephrase that or recontextualize it in a way that makes sense for something that is rotating. Because like I said, no longer is it moving horizontally. Now you can think about an object maybe moving at a certain point along it, like a certain distance it's rotated, but that doesn't really make much sense for an object that is, again, rotating. Distance can be a little bit vague because if you're talking about the very edge of something, then that distance that it travels is going to be much bigger than if you're talking about at the very near the center. Yet, the motion of those should be similar. So, what would make a little bit more sense? Well, we can consider the angle it was displaced. So instead of talking about the actual distance, we can instead talk about how many degrees it was moved over. How much did it actually rotate? If you recall, for a unit circle in math, we start at 0 degrees and it goes all the way to 90 degrees for a quarter turn, 180 degrees for a half turn, 270 for a 3/4, and a full 360 degrees for a full turn. One other thing I do want to point out, actually I'll say this in a second. So angular displacement is going to be represented by a theta, which again makes sense. It's referring to how much of an angle it moves. So why not use theta? That's pretty much it. And the thing that you have to realize about the angular displacement is that we're not going to use degrees. So even though I used degrees in my initial explanation, the angular displacement is actually going to be measured in radians. This is to make a lot of the equations that we have work out a lot better than degrees. Degrees just kind of make things really messy. All right. So this is going to be our first rotational term, is this angular displacement. Now, if you recall, in math, there actually is a way to figure out what the linear distance traveled is based off of how much of an angle it makes. Now, while I said that it wasn't useful all the time, it doesn't mean that it doesn't have its own point. So sometimes it is important to know how much something has linearly traveled, even though it's moving in a circle. Though rotational displacement is still important when you're talking about the object as a whole. So what we're actually going to say is S is going to stand for linear distance and displacement. You'll see why in a second. S is sometimes called the arc length. And if I want to know what this arc length is for a given angular displacement and knowing the radius of my circle, or how far away that point is from the center, I can use this equation, S equals theta R. Now, Few things that I want to note is first, this equation is not on the reference table. This is an equation that you just have to remember. It kind of, like I said, it comes from math. You should have learned it at one point when you're doing some trig stuff or geometry things, and you're trying to learn about arc lengths. There's a few ways to remember this. Typically, one of the ways that I think about it is that this is in meters, and this is in radians, which is not a real unit, which means that I have to do something to this in order to actually get it into the same unit on the left-hand side. So in order to do that, I have to multiply it by the radius, which is measured in meters. It's a little shorthand that you could remember for a lot of these things that for the most part, you're going to end up having the linear term on one side and the angular term on the other. And then r is going to be thrown in there somewhere on one of the two sides. And you just have to remember that. Now, another thing I want to point out about this is that this is going to be the first equation that I mentioned this for, but we actually have two different sets of equations. So this is the first set, which is a conversion. A lot of times what you're going to find out is that you're going to end up having to juggle linear measurements and angular measurements together in order to solve your problem. So when you are given information in the linear sense, you have to know how to convert that to the angular form so that we can do our calculations. Or sometimes vice versa. If you're given information about it moving in an angular way, but you need linear values in order to actually solve the problem, then you need to be able to convert that way as well. So this is the conversion equation, essentially, the way that we translate the linear measurements to angular and vice versa. So here's pretty much the main equation that we're going to work on. So pause the video, work itself, and we'll go over in a second. All right, so we have the Earth. We know that it rotates once every day. So the first question says, determine the total angular displacement. Well, there's really not much that you have to do for this. We know that the Earth rotates one full time around, one full rotation once every day. Therefore, it's going to rotate 360 degrees or 2 pi radians. So the angular displacement is going to be 2 pi radians. Part B asks, what's the total distance traveled? So if you're someone on the edge, I should point out that the question should refer to what's the total distance traveled by someone at the edge of the Earth. So if you're at the edge of the Earth, you are going around the full circumference, essentially. But I can use the equation S equals theta r. We know what theta is. We know what r is. Plug those numbers in, and the entire arc length of you moving in this circle with the Earth is going to be 4 times 10 to the 7 meters. Again, you can actually just, if you realize that you're moving along the circumference of the Earth, you could actually see that one full rotation times the radius is the circumference equation. All right, and actually that's pretty much it. I'm going to kind of break this up into multiple parts to make it a little bit easier, but for the most part, you really want to kind of keep track of what's going on and really pay attention to a lot of this stuff because it's really easy to get lost. For the most part, from my experience, this is probably one of the tougher topics that people tend to have the most trouble with. All right, so if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.